And this begins EE 555 discussion on Wednesday, March 5th, 2014.
Hey, so hi everyone. As you can see, I'll be filling in for Angelos today. And yeah, for those of you who do not know me, I am Nachiketas. I'm the other TA. I haven't met many of you, so yeah. Okay, so let's get right into it. So the first question. Today we'll be discussing about the three-stage switches. And essentially we'll be dealing with switching, and we will be doing some sample problems in switching. That's the plan. So let's start with the three-stage space switch. I'll read the question. So consider a three-stage space switch with n equals 16, small n equals 4, and k equals 2. And the question is, what is the maximum number of connections that can be supported at any given time? So we'll do them one by one. So let's start. So let's first define what's a three-stage switch. It can roughly be represented in this form. You have an n cross k switch, which connects to an n by n cross n by n switch, which connects to a k cross n switch. And you have n by n of these, and then you have k of these, and then you have n by, right? Now, so this is roughly how I remember a three-stage switch. Now the first question asks you, okay, the parameters here are n equals 16, small n equals 4, and k equals 2. Now, what's the maximum number of connections that can be supported at any given time? That's the question. Any guesses?
2nk plus k n by n whole square.
Okay, numbers. So it's really simple, right? So you have two. So you can visualize this because you have just two stages in the middle, and then n is 4. So you have 4 stages in the front, and then 4 stages here. So give me a number, not confusing.
8 connection n by k, n cross k switch.
So the n cross k switch, so k equals 2, right? So for each n cross k switch, you can have 2 connections that are active, correct? So you have 4 so 8 there, right? So yeah, that's your answer. So you get 8 connections that can be. Is that clear? Okay. So for k's, maximum number of connections is 8. Let's say you had the same parameters, but you change 4. How would the answer change? So now, 16, yes, for the entire inputs. the all inputs. So now the maximum connections would be now what if you I don't know, let's see, 8. What happens now? No. Yeah, it would still be 16 because you only have 16 inputs coming in, doesn't you have in the middle, right? Yeah, so it is 16. It's the same. So part B, is asking you, for a given set of input and output pairs, is there more than one way with the switch? Use the parameters that are given here, where n is 16, small n is 4, and k is 2. So in general, for a 3-stage space switch, how many ways paths are there for a given input and output pair? K, right? So that's the answer here. So you have 2 ways. That's it. Now, now for the third question, n equals 32, and then we have to compare the number of cross points required by a non-blocking switch. Here's small n's, okay, for all these cases. So let me list down the cases. Is the question clear? Okay. Now the cases are, first of all, let's calculate remember the formula for this? The number of cross points in a 3-stage switch? No, okay, so let's derive that. Remember the diagram? So we have, so in general, if you have an n cross k, how many cross points would you have? N into k, right? So we have n by n, n cross k switches. So which is n by n times nk, right? And then we have 2, so these are in 3 stages. So n cross k switches here, and n by n and n cross k switches here, right? So you multiply that by the number of cross points, plus we have an n by n cross n by n switch, and we have k of them. So you get k times n the whole square. And this is the formula for the number of cross points. Right? So the rest of the question is just plugging in the values in this formula. So I'll draw a table so that you guys have the numbers. And okay. So if you want our switch to be non-blocking, do you know what value of k we would choose? 2n minus 1. Yeah. So this k is determined here already. So that's what 31, 15. And the cross points will be 208, 200. I mean, these numbers for the cross points by just plugging in the values to the previous formula. So that's it. So any questions on the first question? No? Okay. So let's go to the second one. So here we have a 3-stage space switch, and the input line is busy 10% of the time. Estimate the percentage of time, P, that a line between the first and second stage is busy. And we are supposed to find out how N and K affect P, and how this P affects the blocking performance of the intermediate crossbar switch. Go to part B in a minute. So is it clear what's being asked? Is it clear what's being asked? If you guys went through the slides, so here the P refers to P prime, in the slides. Makes sense? Okay. Let me just draw that. So essentially, in a three-state switch, this is an example path, right? P here refers to the probability that this line, okay, and it's given that the input lines are busy sort of 10% of the time. Okay. Okay. Now, any guesses as to how you go with P? Let me draw it a bit more clearly. So you have n of 10. So that's the scenario that we have. We have 10% on each line, and we have n lines, and then we're supposed to find out that this line is going to be busy. Suggestions for how? So let me break this question down. So let's say, what's the probability that for this line, if there is a packet here, what's the probability that it goes here? So on the other side of the switch. So just for the first line. Say that again. P by K, right? So you assume it's going uniformly because you're not given any other. So it would go to this K. That's just for the first line, right? So it's fine. 1 over K. Correct? Now you have n such lines, correct? Probabilities add up, and you get essentially this. And okay, does that make sense? That's the probability that you need here. Now, and the other question. So how does this P affect the blocking performance of the intermediate closed block switch? What do you think? If this P increased, what do you think would happen? With less blocking, no blocking at all? If P increases? Right. So so let's say your P increased. Okay. Now, if your P means essentially that you have more traffic that is going through line, right? So if you have more traffic that's going through, that would increase the probability that it blocks. It wouldn't decrease it. Okay. I heard you wrong. I thought you meant decrease. Okay. So it would increase the probability of blocking as P increase. Okay. So that's that. So let's go to the second question. Put an output line. What's the probability that none of the n by n paths between the input and output lines are available? Well, I don't like how this question is phrased. Implicit in this question is the assumption that k equals n over n. Okay, this is assumed in the question. Okay. Now, given this, how would you calculate the probability? Make the question a bit more clear. So you're given one input and output line, right? So you only need to calculate for this input and this output. You only need to calculate one particular path. And for that path, we know that the probability that there is some packet here is. So what do you think is the probability that that it's not blocked? No. So what do we want here? None of the k paths between the input and output lines should be available. So you want all of them to be occupied, right? And the probability that one link is occupied is given by, correct? Now, So if you want both of them to be occupied for one path, probability that both these links are occupied in one path, just one. Mm-hmm. At least, the probability that at least one of them is occupied. Correct, for this one link. But do you have an expression for that? It's sort of, call these links like, so, one minus p squared? So look at it this way. So you have these links, call them A1 and A2. You have either A1 is occupied or A2 is occupied. Right? Now, and these are sort of independent of each other. Right? Probability that so either of the one is occupied is really just the sum of them. It's essentially just 2p.
Both can also be occupied. Both of them.
But you don't have to consider the that probability that both of them are. So. Mm-hmm. That is one of the cases that line is busy, but okay. So look at it this way. So you have two lines, right? You have two lines, and then you're calculating the probability any one of them is occupied, right? Now, consider one specific. You need to consider just the specific case that either one busy. Okay. So don't consider the case when both of them are going through. For which case you would get, so you as your probability, and then you have k for each input-output pair, right? And then these are independent. So the total probability would be 2p to the power k. The probability that, yeah.
So are the probabilities mutually exclusive?
Which ones?
Are they independent?
Which ones? These p's? Not necessarily. No.
If they're not, when you have to subtract p squared,
So so you're saying you would get 2p minus p squared?
because if they're not exclusive, then there could be overlap.
Oh, was that what you were getting to when you said that both of them could be occupied? That's a good question. So let's compute it. So what do we have? So we have these p other probabilities are can be occupied, and then p of, if you call this A2, p of A1 union A2 would be correct? Now this makes sense. This is 2p minus p squared. As you said, if you assume both of them are independent and not mutually exclusive. Okay, so let's go with this expression. In fact, the exact expression is irrelevant. Since you get the probability that this is busy, okay, so call it like say call it p prime. That's the probability that the line is busy. Okay, now from here on k paths, correct, and then the probability that all of them are busy would be p prime to the power k. Correct? Now, I will verify this. Let me verify this expression. I'll put up the corrected version up on Blackboard. Any other questions regarding to? Okay, we are running out of time.
People have also seen this probability that both the link 1 minus
Mm-hmm.
probability that both the links are idle, right?
That both the links are idle.
So it will be like 1 minus of idle.
So what would that expression be? So you want to calculate 1 minus the probability that both are idle. So if you assume end up with the same expression that we got here, right? Yeah. So yeah, so I and then I'll get back to you guys. Okay. All right. But once you have probability for one link, the other k links are independent, and then you can get that probability to the power k is the expression that you want. Okay. Any other questions? Okay. So question 3. Consider a cell switch positioning a customer side and a public ATM network. The switch has 4 input links on the customer side, each with 155 bits per second, and then one OC12 link, which is like the other link. And this is bidirectional on the public network side. The OC3 links have a raw utilization flowing from the customer towards the public network, and the OC12 link has a raw utilization of sending the network towards the customers. And this traffic is distributed evenly among the 4 customer-side interfaces. As the time to switch a cell is insignificant, and all cell streams arrive according to a Poisson process. The first question is, what is the slot time? What is the slot time and mean delay at the customer-side interface? As this answer in seconds. Did anyone understand this question? I'm just reading it. I mean, the first time I read it, I did not understand it. Yeah. I mean, this is marginally helpful. So what's happening is you really have to, so one going from the customer to the public, and then another flow coming from the network to the customer. I mean, think of you browsing, okay? You have packets flowing in and going outside and then coming in. So you're trying to calculate delay on each flow, or each, Your packets are going into the public network, and you're trying to calculate delay when they're coming in. All right? Now let's look at the first one. So what is the slot for? Here what are we looking at? We're looking at the customer and the public network interface. So we're looking at going towards the public network from the customer side, right? So what would be the slot time for that? Oh, wait. Oh, did I get that wrong? So let's say you have flows that are going from your side. You're the customer. You have flows going from your side to the public network. Where do you think the delay would be? Or would it be here? So you're the customer. So it would be, right? It would be the network link that would give you the delay. So the question here asks for the customer side interface, and so you is coming into coming to the customer, right? So if packets are coming to the delay at the customer network interface, and if packets are flowing to the public network, you would have delay at the network interface. Okay, does that make sense? So for part A, we are dealing with packets that are coming in from the network to. Okay. Now, with that in mind, what do you think? What do you think is the slot time? Oh, so you might want to keep in mind. An ATM cell size is so that's part A. So, any suggestion you think would be the slot time? For the customer side interface. So what do you want to transmit in one time slot? You want to transmit an entire ATM cell, right? The data that you need to transmit is a constant that's essentially 53 cross 8 bits. And now, yeah, so the only thing is you divide the speed that you have to get the time you take to actually transmit that cell, and that is your slot time, right? And since you are the customer, you get the OC3 bandwidth, which is 155.52. And this turns out to be 2.73 microseconds. So this is your service time, so to speak. Now, okay, so before we calculate the mean delay of do you think this is supposed to be modeled as an MM1 queue or an MD1 queue? An MD1, right? Good. Because in time for us to transmit the packet. Okay, so now rates. So what are the arrival rates? Before we go there, so it says each link the OC utilization of 70%. This is given, and each OC has a utilization of like 50%. So that the traffic coming here is distributed in links. Okay, so pick any one link here. Let's say, what would be the average arrival rate according to you? Call this rate. Yeah, we know this rate. This rate is 4.52. Could you say that a bit louder?
The time is 23 o'clock.
Right. By 4. Exactly. You would estimate the traffic coming on this link and then divide that by 4 to give the traffic on any one link. Does that make sense? So let's do that. So in math, that the average traffic on the OC12 link is 0.7 times your link capacity. You're distributing this evenly across all 4 links, so you multiply that by 1/4. You get 0.7 times 155.52. That translates to how much? Oh, I made a mistake here. So what's our row? the lambda times the service time, right? So let's do the math. The rho approximately comes out to, so what's our service rate? So what's our mu actually? What's our service rate? For this problem. Say that again. So this is actually the slot time. It's not the service time, right? I made a mistake there. That's not the service time. That's the slot time. So so forget about times. Right? It's easier to look at rates. So you're given a pipe of speed 155.52, the rate at which bits are being transmitted, and that is your service rate. So, correct? That you're getting. So what would be your rho? What's your utilization? If you know that your lambda is 0.7 times it's 0.7. So you get your utilization to be 0.7. Well, if you use 0.7 and you know what your mu is, and we know that it is an MD1 system, now it's a question of figuring out, it's a question of remembering for an MD1Q. Does anyone remember the mean delay? Okay. So I'll just give the expression to you. It is given 2 minus rho. Yeah, I don't remember. No. The only formulas I remember are for MM1Qs. Now, to evaluate this expression, we have all the values, right? So you can just plug numbers in, and then you would get 5.915 microsecond. Okay. And that's the mean delay for the customer and the customer side, okay? So for part B, we have had to find out the slot time and the mean cell delay at the network side interface. That's here, okay? It's basically the same. It's the same sort of evaluation. So now we are dealing with the OC12 link, and then we have mu 4 times. And then you get slot time to be, and guess is going to be this, and guess is what this is going to be. It's really similar to the previous thing. Upon the 4 times. The previous value by 4, right? So the previous value, if you guys remember, was 2.73. By 4. So you would get, and then rate. Arrival rate here. Okay, let me write that down. Go. Mm-hmm. Okay. Okay. So can you explain this? Where did you arrive at this expression? Let's see if I can. Yeah. So you have four input slots and utilization on each of them, right? So you have 4 input slots and the total aggregate capacity is this, and you have 50% utilization on each of them. That's it. So that's That gives you your lambda. And so we have a mu and we have our lambda. So what's rho? It's direct. I mean, you can see there's directly half of your service rate, right? So you have rho equals 0.5. And the mean delay is given by the same formula as before. So 2 mu. And you can plug in the values and you would get 1.02 microsecond. Okay? All right? Any questions regarding this? Okay. Now, this one is a bit tricky. C says, what is the overall mean cell delay of the switch in seconds? And we have to express, seconds. So what do you think the mean delay of the switch is in total? So let's try getting an expression in terms of just variables for now. So delay on the OC3 links. And we know what's the delay on the OC12 links. And you're given link utilization on each of these links. So you're given that this is the link utilization on OC12, and then 0.3 is the link utilization on the 3 link. And you have 4 of these, and then you have one of them, and one of the OC12. So .5, yeah, sorry. So take some time thinking about why. So come up with an expression for what's the total delay. What would this be? Say that again. So are you saying this? Each of the lines, right? So are you saying this? So any modification? 4 into TOC3? Okay. 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 And then? Okay, I mean, that's one. So do you think this is a delay? Is it divided by anything? By 5? Any other suggestions? I mean, so this expression doesn't look at the utilization, right? How many packets are coming in at each link. So if you had 0 packets that were going through to, let's say, packets going from your customer side to the public end, in which case one part of this won't be used at all, right? So TC12 would totally go off the picture, because so you wouldn't get any delay from that front, correct? So you need to bring this into the picture. Okay. Oh. Out of time. Let me give you the expression. Does anyone have a quick answer, a suggestion? Yeah, essentially it's that. So you multiply each delay by its utilization, and then you're good. But then you have to be careful. The TC12 link, the OC12 link, you multiply by the utilization of the O3. Did that make sense? because that's through that OC12, and that's how you're getting the delay. Does that make sense? Okay. So the 0.5 plus weighted average, so you do 0.5. Once you plug in the numbers, you get this. All right? So let's quickly get to the final question. The final question says, you have to design an in-cross in SDS switch with a space-time space switch and specify the conditions for which the switch becomes a non-block. Follow the same argument we did that was done in class for the time-space-time switch, and clearly identify the number of the definition of the parameters n and k. And cross an SDS switch. The question: how many space switches do you think are there in the first stage? So we have space, time, and space, right? 2? Yeah, so at the first stage, you would have just one space switch, right? So you'd have one space switch, and then, let's say, k time switches in the middle, and then you have another space switch. So it would look something like that. So this is your space-time space switch. And how many boxes do you need, switches do you need for it to be non-blocking? It's again n minus 1. So the argument goes somewhat like this. It is again n minus 1 plus 1. So this part, the space, as you need, if all, let's say n minus 1 lines, you would take off essentially n minus 1 of the time switches, right? The other, so do you have a guess as to where the other n minus 1 comes from? Because if you take the error, you're essentially taking out n minus lines from here too, right? So you have so the last n minus 1 comes from so you have n time slots here, right? So you're multiplexing. So for that, so if in the worst case you would need an additional n minus 1 to ensure that all together time slots were filled, and then you need one for yourself, and that's it. That's how you get it. Okay. Questions? Well, if there are no questions, that's it. Thanks.
This concludes EE 555 discussion on Wednesday, March 5th, 2014.